Okay, folks, in this second half of the unit, we're dealing with an idea called concavity. So we're going to introduce it just visually in this lesson, and then the next couple lessons we're going to develop it a little further. I asked you at some point on a quiz earlier this year about this idea of the first derivative of a function being positive, but the second derivative being negative. Okay, so I want to draw a graph of what that looks like. This was an extra credit question on a quiz. I gave you like a radio sample and asked you to draw it. It was about unemployment. And this is what this function might look like. Okay, so the function is increasing, so this would be f. The function is increasing, but it's increasing at a decreasing rate. So the derivative of the derivative is negative, meaning we're still going uphill, but we're slowly leveling off. That's opposed to a function that is increasing, so f prime still positive, but f double prime being also positive. So this function we'd say is increasing at an increasing rate. So that function might look like this. This is like probably an exponential curve, right? So increasing, and then as x gets bigger, the function increases faster and faster. So this curve is getting steeper and steeper. Okay, so these are the ideas we're interested in here. Concavity is another way to talk about this, and it's related to how the graph looks. So this lesson's super visual. Notice this graph opens downwards, right? And we could even draw like another example would be a parabola that like really opens downwards, right? So this is a concave down graph, we call it. And this graph opens upwards. So this is a concave up graph. Okay, so talking about the trends, increases or decreases in the derivative, right? In other words, changes in the rate of change affect the shape of this graph. Let me see if I can make this a little more visually nice. So this graph opens down, so the open space is down here, right? This graph opens up, so the open space is above it. Okay, so that's what we're talking about when we talk about concavity. We'll do some more specific examples here in a second. We'll develop this idea of what an inflection point is here in a second, but just take a second to like take in these two graphs here. So an example of a concave up parabola. Let's look at our delta math examples. Okay, so this lesson's all visual, and we want to know all the intervals where f of x is concave down on the open interval, -9 and 9. And then it gives you this point to drag around. We'll talk about that in a second. But here's what I want to do is just shade it in. So intervals where we're concave down, it's going to be everywhere the function opens down. So that's going to be this region, right? And then, so this region opens up, right? Actually, let's do this. Let's make yellow our concave up regions. So the most important thing for me for this lesson is that you can see the difference here. And then we'd say like up here is concave up, over here is concave down. Okay. So take a second to look at that. So purple is concave up, purple is concave down, and yellow is concave up. And again, this relates to the second derivative or the rate of change of the rate of change. Okay, and notice these intervals don't correspond with the minimums and maximums anymore. So minimums and maximums only deal with the first derivative. Our solution here would be, well, my purple zones, so -5 we'll use parentheses for all these intervals, -5 to -1, and then from 1 to 4. Okay. The title of this lesson is Concavity and Inflection Points. So let's talk about what an inflection point is. Inflection point is anywhere where the concavity changes. Okay. So these spots are inflection points. And at those points, the second derivative is equal to a certain number that I bet you could guess. So we will do just one more, and I will talk about the draggable point on delta math for this one. So in this case, we're looking for inflection points in the graph of f, so what we were just discussing, right? And I'm going to do the same thing for this one. I'm going to start by just shading in concave down regions versus concave up regions. And sometimes these are it's hard to see where the exact boundary is, so that's what this draggable point is there to help you for. Like this one's about here. The other regions open up. Okay, so it looks like concave up regions in yellow, concave down regions in purple, right? I'm going to show you what it looks like when I drag this point around. Okay, so what it does is it draws the derivative for you. So you'll notice like the zeros of the derivative in red correspond with the mins and maxes of the function, as we would expect them to. And let's see. Let me grab this real quick. So what we should notice here, let me see if I can draw it. We should notice that the inflection points correspond with the minimums and maximums of the derivative. Okay, and it's not exact because I didn't line it up quite right. So the reason that they give you this is so you can figure out the exact boundary. So here we'd say at x equals -6 is an inflection point, and then here's another one. So this one's pretty unclear to me. It looks like it turns out that inflection point is at equals -1. Okay, and then my next one's at x equals 3. This one was easier to see for me. Okay, so the key takeaway for this is this. So inflection points occur at mins and maxes of f prime. Okay, so if it's unclear to you what the concavity is, just from the graph, drag this point around and take a look at the graph of the derivative, and you're looking for the mins of that.